All right. Hey, everyone. My name is Sandeep. I am a developer advocate at Google, working on the cloud platform. And today I'm going to talk to you about building scalable microservices, gRPC, Kubernetes, and containers. Oh my, right? So, have you heard of our Lord and Savior, microservices? No. No, you have not. If you have joined the church, you're not alone. As you can see some Google Trend data here, people are getting a lot of interest in microservices over the past few years. And if you've been to talks here past 3 days, and a lot of people have talked about microservices, but just a little recap what a microservice is, it's basically taking the Unix philosophy and putting it into your application design, right? So write things that do one thing well and work well together. So now write your applications that do one thing well and work with other parts together, put these parts together, and then you build your application, right? So why microservices? There's so many reasons why you want to do it, and in 20 minutes I cannot convince you to move your monolithic app to a microservices architecture. So I'm not going to try that. But rather I'm going to give you one way on how you could do that, right? How can you actually build a microservices architecture? So I work at Google, and at Google we do a lot of software, right? Search, maps, mail, too many M's right there, are all built on a microservices type architecture, right? That's the way that Google is able to scale this up to ridiculous numbers of people. And how we do that is everything at Google runs in a container. So all those apps I talked about, even map reduce jobs, our file systems, all of this stuff runs in containers. In fact, Google launches over 2 billion, that's with a B, containers per week, right? That's a lot of containers. So how do you schedule all those containers? How do you make sure they all talk to each other? That's where Borg and Stubby come in. So Borg is Google's container orchestration service, and Stubby is the way that these containers talk to each other. It's the RPC framework. Well, that's great. That's what Google uses. What can you use, right? So Borg and Stubby are great. They're old legacy code, and we wanted to make these open source. So one thing we could have done is taken that legacy code, thrown it on GitHub, say, woohoo, open source, and then leave it at that. But instead, what Google wants to do is actually work with the community and build these from the scratch. So Kubernetes and gRPC were born, right? And these are from scratch implementations that leverage a lot of the knowledge gained from the past decade of running containers at scale. So let's start with Kubernetes. So Kubernetes is the container orchestration and scheduling part of this microservices architecture, right? So if you don't know what a container is, raise your hand. Good. So basically, you have an application, right? Let's say you write an app, you put it into a Docker file, you write your Docker file, you create a Docker image of that application, right? So you have basically a fat binary of your application. It works great on your computer. It'll work great in production because it's Docker. And so now you want to use Kubernetes to ship this and scale this out. How do you do that? The first thing you do is create a pod. And so a pod in Kubernetes is a collection of one or more containers. In this case, I only have one, so that's my pod. And this is kind of like the atom of Kubernetes. Now at this point, you want to scale it, right? Running one copy of something is pretty useful when you're developing, but now you want to scale it up so you can actually handle traffic. This is where replication controllers come in. So a replication controller is basically like a state machine. So you say, I want X copies of my pod running. So you can go from 1 to 4, or to 20, or back to 4, back to 5, to 0, whatever, right? And you just tell it, I want X copies of this running. And it'll scale it for you. And the nice thing about replication controllers is if something dies, if a machine goes down, if a pod goes down, it'll spin it back up on another machine, a fresh copy. So it always makes sure so that you have that many copies of it running always, right? So it's not like you're checking it constantly, it's doing it for you. Okay, so now you have these variable number of pods running on your cluster somewhere, right? They're all running and coming and going and dying and re-spinning up. Now, how do you reach those pods? So that's really where services come in. And services are like an API endpoint for your pods. And so it's a static IP with a static port, and that kind of load balances traffic to all of the different pods that are running your code. You take all of this, and that pretty much becomes a microservice in Kubernetes, right? So that's pretty much it. That is like the nuts and bolts of running an application on Kubernetes. I didn't go over cluster management and all that stuff because I'm a developer, but when you're a developer, that's how you basically use Kubernetes. You define your pod, you define your application controller, and you define your service, and you're good to go. So let's say you have 4 microservices running in your cluster. The nice thing is you can scale one up without affecting the others by just doing a resize command. You can scale one down without affecting the others. You can update without affecting the others, and with 0 downtime, the rolling update. And with all that, you've created the Microsoft Office logo, which is not what we started out with, but that's okay. So that's enough talking for now. Let's actually build something useful. So I have this very complicated machine learning program called Hello World. It prints Hello World and doesn't support 3000. There's no JS. If you guys are not JavaScript developers, don't worry, it's very simple. All my code is also on GitHub, so you can look at it later as well. So we're going to build a container. I've already done this, just because Docker does take a little bit of time to push containers up to the cloud. So basically, we're just packaging up that Hello World app into a Docker container. All right, so this is the first Kubernetes part. So this is the front-end replication controller, right? So how do we serve this Hello World application? And so we just write a little YAML file. This is one file split into 2 parts, so it's easier to read. And I've highlighted the important things in red, right? So the name is front-end because it's our front-end server. The image is our front-end Docker image with the 1.0 tag. We're opening up port 3000, and we want 2 replicas to be running on startup. So that's pretty simple. You can see it's a bunch of just labels. That's all this file is. And at this point, we can run this command. And if I do, you can see that so I ran that YAML file, and now I have 2 front-end servers pretty much running in my cluster. All right, so that's great. So now I have these 2 pods that are running, but there's no way to reach them, right? I need a service. So that's what we need a front-end service for. And here, all we're going to do is basically have a mapping from the outside world into our cluster, right? So the type is load balancer, which on, I think, Amazon and Google cloud platforms, it pretty much makes an external load balancer that will distribute traffic to all the pods running in the service. I'm going to map port 80, which is our HTTP port, to port 3000 running on the pods, which is what Node.js is listening to. And finally, I'm going to use a selector called the named frontend, right? So this service is going to distribute traffic to all the pods called frontend, which are the 2 pods that we have running right now. So let's do that. Again, it's just a kubectl create command, and kubectl is the command line tool for using Kubernetes, if that was not clear. That is way too big. All right, cool. So now I've created a front-end service, and you might notice there's an IP address over there, and it's a 10.x.x.x IP address. So that's an internal IP address. Google Cloud Platform is right now spinning up an external load balancer. That might take a little bit of time. Let's see. Don't want to do a watch. There we go. So there's our external IP. So I copy that. And I paste it in. And okay, hello world, right? The machine learning program is working. Woohoo! So that is like the basics of using Kubernetes. You can see it's pretty simple to kind of get something running really fast. Not very interesting right now. I did promise this talk was about microservices with an S, and I just did a microservice, which is just hello world. Doesn't really count. So the other part about building microservices, right? You can run as many containers as you want, but they need to communicate with each other, right? So what about communication? This is how it will typically look. Microservice A is talking to microservice B, talking to C, talking to D. They're all talking to each other. Maybe A is your API endpoint that the internet talks to. And the thing is, when you're having microservices, the biggest issue comes in this communication pattern, right? What was previously a function call in a monolithic app turns into a network call. So when your app starts scaling, those network calls start scaling exponentially as well. So that's a big problem. The best way to solve this is good API design, right? And I cannot teach you good API design talk in a 20-minute talk, but I want to talk to you about gRPC and how that can help you design a good API. So a little bit of background at Google. I did not know this until I actually wrote these slides. There are big O of 10 to the 10th RPC calls per second in our data centers. That's a very big number. That's a lot of zeros. So how do we solve this? We solve it with Stubby. And gRPC is kind of the open source descendant of Stubby. So let's take a look at why gRPC is good for building microservices. And so before I keep going, I want to address the elephant in the room, which is REST and message queues, right? Both REST APIs and message queues are really good. I use them for a lot of things. But gRPC does solve a niche use cases when you're building microservices. So let's talk about those. So the first thing is gRPC uses protocol buffers as its serialization format. So who here has heard of protocol buffers before? All right, good. So if you don't know what protocol buffers are, it's basically, you can think of like JSON but binary. It's a really terrible way of saying it, but that's what it is. It's a binary serialization format that Google's open sourced a few years ago. And basically what it lets you do is define your API in a .proto file. So here I have like a hello request, a hello response, and a hello service, which is an RPC call. And basically you can generate your interfaces from this .proto file in whatever language you're using. So the nice thing here is it serializes the data to binary, so it's very efficient on the line with very low overhead. So now you have this nice binary format. You need a transport layer for it, and that's where HTTP 2 comes in. So not HTTP 1, but HTTP 2. What is HTTP 2? One is its speed, right? HTTP 2, that's the biggest advantage it gives you over HTTP 1 is raw speed. And if you think this is like a fake demo, you can check it out yourself at http2demo.io, and you can check it on your own computer, which is pretty cool. But it does give you a few more things other than speed that I think are really applicable to microservices. So what are those things? One thing is multiplexing. So multiplexing means you're taking a bunch of connections and shoving them into a single TCP connection. Why would you want to do this? Instead of opening a new TCP connection for every single request, you can have just one pipe, pretty much, and send all your requests through that one pipe. Therefore, you're saving on a lot of overhead by not doing that TCP handshake every single time. Bidirectional streaming. So this means no more polling, WebSockets, or clunky server-side events. Instead, you can keep that pipe open and say, hey, whenever a new event comes, send it down the pipe, right? This, of course, gives you a lot of performance benefits over polling, for example. And finally, I think flow control is a very cool benefit of using HTTP2 for your microservices. If your service is getting flooded with requests and it can't handle them, it does not make sense for your client to keep sending more, right? If you had flow control, you can say, hey, slow down. I cannot handle this many requests. And then it'll start uncongesting your network, which is awesome. gRPC also supports multiple languages. Out of the box, all of these, Python, Java, Ruby, C#, Node.js, PHP, Go, C++, C, and Objective-C. What does that mean? What does supporting languages mean, right? This means that there's idiomatic support for these languages, so in Go, you'd use Go routines to do concurrency. In Node.js, you'd use callbacks to do concurrency, right? There are different ways in different languages to do almost the same thing. So the way that you use gRPC is you use a .proto file, you generate an interface, and it's native to that language. So this means you can write your different microservices in different languages and have them all communicate together. So you don't have to be locked into using Java for everything. You can use Java where Java is right, and maybe Go where Go is right, which is pretty cool. And finally, mobile first, right? What does that mean? You might have noticed I said Java, C#, and Objective-C as the supported languages. You can guess which 3 mobile platforms those use, or use those. So why would you use gRPC for your mobile app? Definitely the overhead, less overhead and less data. is a better experience for your customers, right? Less battery life is being used, less data is being used. It's just a better experience. All right, but now let's actually upgrade our app to use gRPC and actually have microservices plural. So this is my .proto file that I'm going to be experimenting with. You can see that I have a package called geo. I have an RPC call called distance between. I want to calculate the distance between 2 points on the Earth. And basically my arguments are latitude and longitudes. They're just floats. So this kind of becomes your API definition. And you can share this interface file around, and so everyone can consume it and start using your API. All right, so now we have a front-end server running. Let's write our back-end server. So the first thing we do is load up that .proto file, and we use the gRPC.build server. Again, this is different in every language. This is Node.js. And we create a geoservice object, right? At this point, we have to basically define that getDistance call. It's like an abstract class in Java, right? You want to write the meat at this point. So all we're going to do is say getDistance. We're going to take in the input and call the getDistance, distance between. We're going to get in the input and call a function called getDistance. What is getDistance? It's just calling the Haversine formula, which is the way you calculate 2 points on a sphere. Simple stuff, right? Again, nothing too complicated. Now, we do server.bind on port 551, which is the de facto gRPC port, and we call listen. And that's it for the backend code, right? So now we've basically built a gRPC server that's listening for requests on port 551. All right, so we're going to build that. And now let's update our front-end code, right? So no longer doing machine learning hello world, but we're doing a gRPC service call. So we're going to load up interface.proto. And now, this might be a little interesting. We create a client, and the server is backend:551. So what in the world is backend, right? There's not an IP address. Where is it pointing to? So in Kubernetes land, right, going back to Kubernetes, backend is actually injected into the cluster itself, right, using DNS. So if you used Docker before and you link two containers together, it's the same thing that Kubernetes is doing, but using DNS instead. So now backend is pointing to our backend service. Okay, so frontend will get a request that looks like this, latitude and longitudes, origin, destination, simple stuff. And it's going to use the function that we defined in the backend code. It's going to call it, so client.distanceBetween, and then print out the response it gets from our backend server. Right, so we have our backend microservice and our frontend microservice, and they're talking together using gRPC. Build it. Okay. So now at this point we have our backend replication controller, right? We got to spin up some backend servers. This looks exactly the same as our frontend replication controller. I'm just going to say 4 replicas instead of 2 because why not? And I'm opening up port 551 instead of port 3000. So let us run that. Cool. So all right. So you might notice that we have 2 front-end pods and then 4 back-end pods. Okay. And now we need a back-end service so our front-end can talk to our back-end. You might notice one thing different from this file versus the last file, which is there's no type load balancer. So this will not create an external load balancer. It's all internal to our cluster, which means that no one else can enter because it's all private IPs. I'm going to open up port 551 and select all the pods called backend. So create that. So now if I do a get services, I have 2 services running, front-end and back-end. And of course, you can have as many services as you want. You might notice that back-end only has an internal cluster IP and not an external IP. OK, so now how do we upgrade our front-end from saying hello world into saying this getDistance function, right, without taking anything down? With Kubernetes, you can do that with the rolling update function. So what this does is it rolls your containers, your pods, to the new version automatically. And you can set the update period to whatever you want. So let's say you have 40 pods running in production. You can slowly roll them up. Now you see your error log going crazy. You can roll it back. And how do you roll it back? You do a rolling update to the old version. That's it, right? So rolling up, rolling back is the exact same process. So let's do that. Okay, so it's going to update one replica, make sure it's running, then update the other replica, make sure it's running, and so on and so forth. I'll wait for this to finish. Okay. And now we go back to our application, which I deleted. Saying hello world, and it updated automatically to our new version, right? And zero downtime, blah, 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 all those buzzwords that you know. And there you go. So that is basically how we updated our app. I think I have a few more minutes, so I'll do one more step. Now let's say we have these pods running, right? Now I'm getting a lot of traffic. I want to scale up my front-end server. How do I do that? I just do kubectl resize what? Yelled at me. That's fine. And now, if I do get pods, now I have 4 pods running, right? So it's that easy to resize your pods, and it's almost instantaneous because it's containers.
Question?
Yes.
What's the best way to maintain things like session and state between these?
I'll answer that right after I finish. I will just finish it up. So yeah, almost finished. 1 more minute left. If you want to learn more, if you like my talk, if you didn't like my talk, that's fine. I want you to go and try it out, right? Because it's open source, can run on-prem, in the cloud, wherever you want it. kh.io, gRPC.io. I gave you guys a short link, so it's easy to follow. And here's the product pitch. If you guys want to try it out easily, we have a commercial product called Google Container Engine, which runs on the Google Cloud Platform. With one click, you can create your cluster and get started with Kubernetes. That's what I was using for all the demos. If you want to go deeper into the code, I have it all up on GitHub. Here's the GitHub link, and it's very long. But yeah, please, guys, use it out, fork it, contribute to it. It's written in Go, which is a great language. It's open source, so just make it your own, right? And if you have any questions now, I will start answering them. Thank you, guys. So your question was, does it have caching or
just how do you maintain state between all these instances? So you got 10 that you're running right now. And if I was making one call, say if I have a shopping cart.
So how do you, okay.
Is there like a better strategy than just putting some kind of external cache like Redis?
That would probably be the right way to do it. So you use Redis. I'm not sure if the load balancers may guarantee that you're going to hit the same endpoint, because in Kubernetes land, the whole point is something can go completely down, and your end user should not even know that that happened, right? It'll bring it straight back up on another machine if it has to.
So for trace state, I would have to build that into my application.
Right. So Kubernetes uses like etcd, or you can use Zookeeper or something like that to share that kind of stuff. But using something like Redis as a cache would make a lot of sense for keeping shopping cart state forever.
How, for the backend services, you didn't have a load balancer.
Yes.
So is that client-based load balancing?
Okay, yeah, so that's a little bit confusing. I should have made that a little clearer. So the type load balancer, it only really works on cloud platforms. So I think Amazon, us, Google, and I think Azure now supports it too. It creates a network load balancer on the cloud platform itself. And that allows you, basically gives you an IPv4 address that the outside world can hit, right? If you don't have a cloud platform running on-prem, you just open up a port on a machine and use Nginx or something and load balance it that way. Now the backend, you're right, it didn't have a type load balancer. So that's Kubernetes itself is doing the load balancing internally in the cluster only, right? So it's a cluster service, and that's the load balanced by Kubernetes. So you're not running anything special there. Kubernetes is actually doing the load balancing for you. Yeah. So it's built into the thing.
So is there, with the gRPC stuff, is there any client-based load balancing where it knows, it discovers the service instances, right? And doesn't have to
So I'm using Kubernetes to do the service discovery for me. So you saw in my Frontend Code, I had Backend colon 551. That backend is DNS that's managed by Kubernetes. Or Kubernetes is injecting DNS into the cluster. So it's saying, what is backend? And then Kubernetes is saying, hey, use this IP address, right, on the fly. So gRPC does not know anything about.
They're working on client-side load balancing in gRPC, but I don't think it's in there yet.
Yeah.
Okay.
I'm looking at GitHub.
Yeah, so everything is public on GitHub. Like, yeah.
Yeah, I kind of find interesting on gRPC here. Everybody's talking about this conference, JSON, REST, and then you were mentioning binary format.
Yep.
This is a shocking.
Yep. Yeah, so I think a lot of people in this conference are doing external APIs, right? So they're trying to have someone else consume their API, like APIs as a service, right? And for that, I think REST and JSON is like the de facto standard because it's so easy to understand and it's so easy to debug. And it's clear text, right? It's plain text on the wire. With gRPC, it's really better for something like a microservice where you care about performance a lot more, and it's all your developers, right? You define the API, it's your API. You define your .proto file, and you share it within the company, things like that. So it's a lot more applicable to microservices than, say, a public API, where I think REST pretty much is the de facto standard.